Go to the library. Yeah, he said it was. No.
That wouldn't matter.
How's it going, Mr. Butters? How are you?
She's like,
Nora, we tried something.
No homework due yet.
That's the only homework I have right now.
Jason, can I see you there?
Yeah.
Okay. I did that last semester.
The first exam's pretty rough.
So will all the homework we have be assigned out of a book, correct?
Yeah.
So like we'll need to actually have a book to be able to access like the homework, like to find problems. Or like will you like post like the like
I'll try. I'll try to maybe. Primarily, I was doing like assign just the numbers of the questions in certain documents. But if I see like the people do not have access and they cannot really get the book, maybe I can make a PDF document writing the questions. But primarily, I try to use the book.
Gotcha. No, I was just curious.
Did you get any version of that?
I found a 6th edition, but I was trying to. I couldn't find a 7th, which I know is the newest one.
It's very close to the 7th one.
They're both pretty close.
It could be used. Yeah, you could use it.
That should be fine. Okay, cool. All right, thank you.
All right, let's start. So, Springfield people, can you hear me? Anyone from the at a
Yeah, I
distance
can hear
studio?
you. I can hear you.
Okay. this time, anytime you feel like I'm having a moment of silence, let me know. Or if you have any question, just interrupt me because I can't see the chats while I'm opening the PowerPoint. Okay? So today we will starting with our first chapter, which is the introduction. Basically, we'll get into some information about the history of power systems and how they have evolved. We'll get into some of the current and future trends in power systems regarding to its technology. And we'll describe a little bit the structure of the electric utility industry and some of the standards that govern that. And finally, we'll go over the Powerworld Simulator. We'll just introduce it for you to make you aware about the different functions there or capabilities in any power system software. So, about the history of power systems, who knows who made the first trial regarding to electricity? It should be something obvious. Thomas Edison. He started with the light stuff, with the DC systems, so he receives the credit for that, definitely. Shortly after that, they started forming something quite similar to the utility industry, which we have today, but that happened in 1882. And since then, we have been seeing quite a remarkable advance in power systems utilities. Basically, after World War I, when we started to have that industrial capabilities, and then shortly later, like in 1970s and 80s, when the capabilities of control and automation started to be formed. So that really made a boost for the electric utilities. Here we'll go over a few forms of electric power generation, which started by the time. So initially, we had just the DC systems because it's mostly linked to batteries. So that was the first form of power generation. And they were able to start working on the DC motors, which was the first form of power generation. And then shortly after that, the AC systems start to evolve because by the advance of transformers, now we are not limited by the DC sources. We could really change the AC power now into different levels by the help of the transformers. And after that, shortly also in 1891, the steam-driven generators were in market. And they are still, till now, the most common type of generators that are being used because they try to convert the thermal energy into mechanical energy and then into electricity. Another common source, which is the water wheel-driven generators. It's everything related to the hydroelectric power. This is common in areas when we have some good rivers with good flow. And I think it accounts here for like 7% of the total electricity generation in the US. Although it's very good type of resource and very clean, but it has many issues with having some constant flow of water, which is hard to make because normally in the winters we have very strong flow. So we'll have a lot of power generated from the hydroelectric sources. But during summer, the flow gets really slow and that power may not be strong enough to turn on the turbines and other things. After that, but definitely not in 1990s, quite before then, natural gas was started to be used as a resource and it's quite competitive in market with the other steam generation things for a reason that natural gas was abundant in many areas and it's quite efficient in combustion. Did anyone take thermodynamics or heat transfer? So I had similar stuff when I was undergrad. So I understand how those cycles go, the combustion cycles, and so it's a very clean and good resource, the natural gas. After that, we had the nuclear revolution. Uh, Nuclear power actually is a very good resource, and you could generate huge amount of power by nuclear resources in comparison to other ones. But its main issue is the safety. Uh, we had some incidents in different places around the world, and they were associated with nuclear units, explosion or incidents, faults. So it becomes quite risky. Um, Actually, before coming here, I was considering going to France to do nuclear power generation in a PhD program. And they had two tracks, decommissioning and waste management and nuclear power generation. So 80% of the students were into decommissioning and waste management. So I found no clue in enrolling in nuclear power generation because I'll have no future in the industry. I would be just doing maybe some research, but that was not really my career goal. So anyhow, there's a huge shift now from nuclear into other clean resources because of those issues. Uh, our newest forms are the renewable energies like solar, wind, and other new types coming into the market. They tend to be quite clean, but they are quite expensive to start in. So the initial cost is really high. And in many areas of the world, they are mostly concerned by having power. They don't really care that much about the environment or other things. Anyhow, now there have been major effort in industry to make the solar panels, let's say, as much as affordable as they can give it for us, and even the wind turbines. And the governments, some of the governments, are trying really to support those initiatives by giving some incentives to the people. But there's a major issue with renewable energies. They are not consistent. So there are some days of the year where the grid will be overloaded by the solar and wind power. And many other days, we could have a zero input from them. So for power quality and stability issues, this is not good. Actually, they could be seen as a fault from the grid side, the renewables, because whenever they are integrated, we'll see a lot of fluctuations during the day, depending on the irradiance and the wind strength. The last promising technology regarding nuclear energy is the fusion. Does anyone know the difference between fission, fusion, and nuclear power? Okay, so you basically don't know that thing. You're not from nuclear. Yeah, so this is the common difference between the two, but in nuclear power generation, they are into fusion to generate as much power as you can from those small protons or so. So there's a note about various frequencies. So the early AC systems operated at different range of frequencies like 25, 50, 60, 133 hertz. But now most of them are quite obsolete because a few countries use like the 60 hertz, while the rest of the world uses 50 hertz. This is by convention. I don't know why they chose the 50 here and the 60 there. That was quite an agreement in the industry to use that standard. But why do you think in the early times they had multiple frequencies? And they even had more than those. Yeah, they were not interconnected, but there was one more important reason. There was no regulators even at that time. The main issue was whenever someone like Edison is trying to work on a motor, he do it on his own thoughts and standards, and another person he's generating power from another way. So it was quite dependent on the equipment that you are using and its output, and they did not really have that the capability of power conversion and rectification, conversion, transformers. They were not available, so they were not able really to shift the voltages and the currents from a level to another one. So they would provide what they have on hand. The frequency of the generation is equivalent to the frequency of the delivered power. So that was the main reason why they had multiple frequencies. But after the growth of the transformers and so they tried to unify all the grid and make it quite interconnected. So even though I'm having my own station in Boston, I was required to have that transformer which boosts the voltage into 110, let's say. Even some other guy in Dallas had some other generator or type of motor. So now here they are talking about the rate of growth of electricity generation. It has been quite steady into the up direction since the 1902 to 1972, definitely by the population and industrial growth. Although we had some moments like during the oil crises where we had some slowdown in demand, because if there's no oil, most of those thermal units will not be able to work and generate power. Also, the increase of load growth have led to an equivalent increase in the generating unit. So the power system works in a way that the number of resources or the amount of resources should be equivalent to the amount of the loads on the system. So this is quite related to the demand response. So if I have a need of 50 megawatt, I will not generate 100 megawatt and waste 50 of them. I'll be generating 50 megawatts or 52 megawatts, including some losses here and there. But as I'm seeing a lot of demand, a lot of need, they had to recreate or restructure the grid and include many more generation units here and there. So any questions so far? Let me check the Zoom people. So any question? So I see everyone here. Actually, I see a few missing people here, but 5 students sent me messages today about different things. Athletics, going to the airport, being sick, and I told them this is totally fine. So yeah, I think I have 5 people who had some excuses today. That's why I see a few missing people. Okay. So now we'll move forward into the technological developments that are happening right now into the grid. By the way, all those are from the chapter 1 in the book. But there's here a summary of all those details. So in any case, if you are more interested into the history or you'd like to get more details into each of those things, you could really check the book. They have a lot of information about them. So here's a list of the most common technological developments right now on the grid. We have the suspension insulators. Does anyone know where we could use those type of insulation thing for suspension? One? Or where? Yeah, definitely. On the poles, actually. Because did you ever see any disc or a group of discs on the poles, mainly on those wooden ones? Those are used for installation because at that moment there might be some junctions or connections. So they really want to make sure that there's some insulation at that point. Otherwise, the electricity might flow out from that junction or so. And sometimes those insulators, they are made from some type of material. It's like the glass at some time. And then they made it a metallic or so. But anyhow, if it breaks down, you'll see some fire at the pole. One more thing is the high-speed relay system. And we have down there also digital relays. Why do you think we need relays? Relays. Did you take any PLC course or automation? No, actually relays are just for sensing. They just do sensing, and they send a message to the circuit breaker or other equipment that there's something wrong here. So at first they were quite mechanical relays. They were not that efficient. Now they are more into those high-speed PLC things, the digital relays. They are much faster. A relay is used for sensing. Actually, those are quite important things you need to know, because if you apply for some internship, they'll ask you similar questions. Why do we need a relay, or what's the difference between a relay and a circuit breaker, things like that. What about the extra high voltage circuit breakers? Extra high voltage, it means that we use them at a very high voltage, which is like 2000, 3000 volt along the transmission. Not here. Here it's like a distribution network. So what's a circuit breaker? Exactly. Whenever a relay is sensing some very high measurement, the operator would know that there's something wrong there. So he trips those circuit breakers. So he's just opening the circuit and prevents more current to flow within the system. What about the reclosures, high-speed reclosures? Those units are used to interrupt that faulty current. But their main difference from the circuit breakers are those, like, they open and close like couple times in a way to interrupt that faulty current. But its function is quite temporary. The circuit breaker is permanent. So at first, whenever a relay is sensing something wrong, the operator should run, or there should be some automated communication to the reclosure to open and close twice. So hopefully the fault will be cut, because it's like a message, or it's like a flow of electricity. In case that fails, then another step will be just opening the circuit. But opening the circuit at first could be really bad, because we'll be suspending power on a number of customers. It could be 1,000 or a whole city or a whole neighborhood. So at first they start with the easier things to do. Extra high voltage surge arresters. Why do we need those? Surge arrestor.
Stops like damage equipment.
Yeah, definitely. Thunder and similar things cause really huge spikes. It's equivalent to 20,000 amperes being fed into the network. They could burn everything. So those surge arresters are found on the poles sometimes, and they are connected to the ground. So whenever we have a fault or such thing, that huge amount of electricity should flow into the ground, which is a typical place to throw away all that power, instead of traversing on the transmission line. Power line carriers, microwave, fiber optics, those are quite new things into the transmission line to make it more smart, faster in communication along the grid, so that we could transfer all those information about currents, high current measurements or so, in the fastest available way. Because in power system, we look into a portion of a second or so, or even less. So if we need to wait for a few minutes for a thunder alarm or so, we'll have the whole city burning by then. So those advances in communications are quite helpful. Installation coordination relates to the levels of insulation we should have on the grid. We should have at first some primary protection, and then secondary, and then if needed a tertiary protection. But primarily when a fault happens, where do you think is the first level of protection should be? The primary, secondary, or tertiary? Yeah, definitely the primary. In case it fails, we go into secondary protection. In case it fails, we go into the tertiary if needed. Because whenever we get far, it means we are isolating a larger section of the grid. So this is not good. We try at first at the smaller range of area. Energy control centers, those are related to automation. We want everything to be automated and under control. So those are the purpose of those things. And we have talked also about digital relays. So this is basically about the technological developments. In 1954, high voltage DC transmission line was put into commercial operation in Sweden. So what do you think is the advantage of that?
Some efficiency issues because, like, since there's a complex trying more power from there's swings in power. So you have eddy currents, lines, effects, outer ring of whatever your cable is.
Okay, very good. But what's the difference in high voltage DC? We still have a transmission line, and it has the same issues actually. It's still a transmission line. But what's the advantage? How we could recover from that efficiency problem and so? I need to calibrate this one every time. So the main issue with efficiency, you said the right thing, but the advantage of, oh, I need, it's not working. So let's get back here. I was trying to write something, but it does not look the pen is working. So the main advantage of high voltage DC, U is equal to Ri, the voltage. In high voltage DC, we try to, let's say we are concerned about the I, because the losses in the system, what's the loss? Which is Ri squared, the lost power during transmission. So it's equivalent, it goes with the I squared. So in order to decrease the loss, we really need to decrease that I squared. And the proper way to do it, if U equal Ri, we really need to make R is stable, it's constant, it's not changing. And I'd like to decrease the I. So the proper way is to increase V. By increasing V too much, I'll make the current too small, and then R is still constant. So at high voltage DC, I'll be calculating Ri squared it'll be very small number. This is how we minimize the loss during transmission using high voltage DC. So as much as we increase the voltage 10 times, 50 times than the normal level, we are reducing the losses by 20 times squared or so. So that's a great advantage for the transmission. And here they are saying that studies have shown that overhead transmission is economical and transmission distance is longer than 600 kilometers. So it means that doing that.
I think we can't hear you again.
Can you hear me now?
There we go.
Okay. So at transmission, let's say at Texas, they have 600 volts, and from here is 400. So a typical way is to have a transformer to boost here the voltage into 400, keep it at 400, and at Texas, the received voltage will be 400, and then we step up with another transformer to 600. So in that way, we'll be connecting two asynchronous networks in quite an efficient way. We just need couple transformers at the ends of the transmission line. Utilize long underground or underwater cable circuits. It's an option that we don't really need overhead transmission lines. Like most of those are overhead. But in some areas, you could transfer like under Lake Michigan, let's say, where I had a visit. From one side, from Wisconsin to Michigan or so, under the lake. To bypass the network congestion, this could be like in Manhattan or so, in very highly populated areas when there's a lot of demand, and it's not really nice to see all those transmission lines around the skyscrapers, so we get into underground transmission. To reduce fault currents, definitely, when you have that very tiny current flowing, the issue of faults, in case they happen, they'll be much less harmful for the system because we'll have a very tiny current. The level of current is very high. So that means the fault will be less harmful for the grid. Sharing utility rights of way, the usage of the network without degrading the reliability and mitigating the environmental concerns. Those are also some good advantages of high voltage DC. So now we could see the interconnected transmission in the US. We see a lot of crowd actually in the Midwest area, maybe in the Northeast a little bit. In Texas, there's a lot. But in some states, or some cities, Las Vegas has none actually. So anyhow, those are listing here the high voltage transmission lines. Definitely, you could see the order of voltage. It's in the order of kilovolt. Yeah.
So with the HVDC, like because they bypass network congestion, when it Los Angeles, like Los Angeles, like there's a big city that high voltage DC.
Yeah, but we could transfer energy to there using high voltage DC, but at the last moment, there should be some substation where they step down that voltage at some moment for distribution purposes. I cannot go over neighborhoods in Los Angeles using high voltage DC. Because for distribution purpose, if you have a house there, we cannot really make a substation right next to your house. So usually they will ship the power to some vacant area around Los Angeles, and from there you should have some substation to step down that very high voltage for distribution purposes. But high voltage DC is common, like if we need to transfer power, I know from Washington State and Oregon, because they have a lot of electricity, a lot of rivers, they typically ship electricity to Southern California from there by high voltage DC. So there's a thing here on this map is that it's showing how all the US is quite interconnected. Even though we have regional systems in Texas and here and there, but there's still some interconnections between each unit of those. For the reason is that in case Texas system gets into some problem, they could really easily open those interconnections and move in some available power from those Great Lakes area, let's say. So they are saying you could schedule power transfers during normal periods to take advantage of different reasons. Like now electricity is being dealt as a commodity. So there's something called an electricity market. So it could be quite more economical for me to buy power from Arizona, because they use a lot of solar there, than to generate power in this state. So they could ship at certain times using those interconnections. So this is the great advantage of interconnected systems. The present and future trends, there's definitely a large long-term investment and planning decisions being taken at the utilities level, because they have things in their mind, like by 2050 or 40, the current grid cannot supply all the increasing demand. And now with those Bitcoins and all that mining and all the different type of industrial activities happening, they are witnessing a sharp increase in the need. So there are some major efforts into improving the transmission planning and creating more units and attaching that to the system. So what's the type of transformations you are seeing on the grid? There's some different new types of resources being added, different sources, geothermal, solar, wind, and within each of those, there are multiple types. New technology options, and a change in customer expectations. I would give an example of a new demand on power with those electric cars. Many of us now are adopting the EVs, and those are really bad for the grid. Although we are trying to save the environment, I'm not sure about that, but they claim that discharging process has a large effect on the grid. We are not talking about single car or 10 or 2. At some moment, we'll have millions of cars being charging. So I've seen a consumption pattern during the times when they are charging. You'll see large dip on the system because there'll be millions, maybe tens of thousands of cars all charging at the same time. So the growth in distribution construction roughly correlates with the growth in electric energy consumption. This is the truth. And there's quite a growing agreement in the power industry that a smart grid technology is the answer for uncertainties and challenges. How do you think a smart grid acts in a way different to the regular traditional grid? Yeah, excellent. We have a lot of more control options on the smart grid, a lot of more monitoring, tracking, the demand response. Let's say those smart meters. If I have some smart meters around campus, I could really know how much efficient is the system at the school. Actually, I had a discussion one time with the utility manager here at this town, and he told me that the whole university spends power from one point, so they have just 1 meter for the whole school. So this is a single point where they can measure, and they send a bill for the university for all those buildings. So I told him this is not really efficient at all. He said, "Yeah, I know, but this is what we have right now." So they are considering of splitting the university, let's say, into multiple units, so and each unit is being fed from a line. So in case electricity goes away, it won't be all the university off of power. So this is a new plan to happen. Here are the advantages of the smart grid: self-healing from power system disturbances. Self-healing, it's not a medical thing. It's more related whenever a small fault happens on the grid. If it's large enough, that could not be noticed sometimes. The grid itself will absorb that fault. So this is the advantage of that smart grid. It enables active participation of consumers in the demand response. So if Owen has a meter in his home and I'm at the utility and I can track his usage and know at certain times that there's a much needed demand, so I could make more informed decisions for the generation. Operates against both physical, cyber attacks. This is a new thing with the smart grid. Whenever we got all that new technology into the traditional grid, now we are suspect to some hacks. So some bad people around would like really to hack the whole grid, know everything on the grid, know all your consumption patterns, and even steal electricity. And this could happen by a simple hack. So there's really a lot of efforts being made at state estimation level in order to increase the privacy of the grid and its security. It tries to provide quality power that meets this century needs. By that, all that tracking and monitoring, we try to make the power quality as best as possible. And it tried to accommodate all the generation and energy storage technologies, because now we have some type of resources, let's say the solar or the wind. At certain moments, they'll be generating a lot of power. But my demand or my need is like just 50 megawatts. So if we are generating 60 megawatts, there's one of two options. Either we throw away those 10 megawatts as a loss, or we store them somewhere. Not in my home, but in some storage systems or large batteries. And then we discharge that power when needed, like during the night, let's say. This is another issue with renewables because I cannot make a battery as huge as this building. But anyhow, some people like in Germany, they like those things. To be enabled to get into new products, services, and markets, we talked about electricity market, and to optimize the assets utilization and operating efficiency of the system. This gets better with the smart grid, definitely, than the traditional one. So here are some of the electric utility structuring system. We have a number of agencies, commissions, regulations, acts issued by the government, which try to regulate the electric system or the grid itself. So here we could see like the Energy Policy Act, which tries to shift and continue shifting the regulatory power from the state to the federal level. This is not communism, actually, but the government is into getting a unified system for the whole United States. Some people in Texas, they say, no, this is our state, this is our own system. But that did not prove to work out because at many times they had really bad blackouts. Even my advisor was called there to go and help on that problem sometime. The Federal Energy Regulatory Commission, this commission also has some work to make sure that the energy market or the electricity market is quite regulated because they are dealing with sellers and buyers. So here at this town, the electric utility buys power from some sellers, and he told me that the utility manager that they are much more into the cost. So whenever they see this is the lowest possible price, they just ship from anywhere. And they're noticing that renewables cost is getting quite less, so they are buying more out of that, not for environmental reasons. And then we have that transmission open access regulation. It has been mandated for the wholesale generation. And that corporation, NERC, this is very famous. It's responsible for maintaining the standards and reliability. So if you get to work at any power company, they would list a number of standards that you should be aware of. And those typically say that, for example, the range of voltage increase should not be more than, let's say, 1% in case of normal operation. So if you make some simulations and then you see at some moments the voltage in your grid is up by 5% at a certain event, that violates the standards. So your plan is declined, actually, or your system or your design. Now we'll discuss a few things about the different power flow programs or software and power systems. First thing that we really need to be aware of is the power flow programs. So power flow is usually a function in the power system software just to obtain the voltage and current magnitudes and angles throughout the grid. This is important to track the usage and the faults. So on a typical solution or a typical software, you'll have 100,000 or bus or so. This is a huge amount of points to track. Let's say if each bus have 4 measurements, this is like 400,000 at every second or every minute. So those power flow programs are really needed. We will get into those in chapter 6, power flow analysis, but at most you will solve like 2-3 bus problems. The other type of programs is stability. Stability deals with investigating how the power system would act in case a disturbance could happen. A disturbance may not be a fault, actually. Sometimes if I'm turning on a generator, it will absorb a lot of power at starting. From the grid side, it shows like a fault, but it's not actually. After a few seconds or a few minutes, the initial conditions or normal conditions will be restored. So stability programs try to ensure that our system will get back into the normal operation after such incident happens. This type of problem you could see in the other 5540 course. They have a very small chapter about stability. Short circuit programs. This is very important because most of the time people won't care about the normal grid operation. They get mostly concerned about it whenever a fault happens. And this is where the short circuit analysis is needed so that we could investigate how bad the fault would be and what will be the necessary protection schemes that we really need to implement. Transient programs are used to study the system at some very large disturbances, like a switching event or thunderstorm or so. So how would the system operate at that moment, and what should be the protection measurements taken from those overvoltages? Like here they mentioned like surge arresters that protect equipment against transient overvoltage. You should run that transient program to make sure if the rating of that surge arrestor is good enough to handle such large over voltage or transient. Here we have this Powerworld Simulator, which comes with the book. I think it's free. Also, there's a free version which you could use. So if we go to the link here, we see here multiple versions. I usually chose the newest one, which was published quite a day ago. I think I can download, but I cannot open it. Just fill in this form and they'll send you a link with the files. Just download it on your laptop or computer. Try to run the program. It's for free. It has a few buses capability, maybe 10. And they have a lot of sample cases, open case examples. Just open a case and run. As I said before, I wish I had the capability here, but I don't have, no one here has permissions to install software on this computer. So it will be hard for us to run here. But we'll figure how we could really at least see a few things of that. So for now, just try to download that software and see how it looks like. Let me see if I still have any slide. And this is the summary for today. This is what we have been discussing. Do you have any questions? Zoom people. Okay, so I think we're done for today. So chapter 1 is over. You won't have an assignment on chapter 1. You should know them because in the exam, I might have a question like true, false, or things like that, fill in the blanks. So you should be aware, not about the dates. I will not ask you when did Thomas Edison or when the Transformers started, but be aware about the topics, okay? There's no assignment on this chapter, and we'll start chapter 2 on Monday.